of noises you expand, sir?
Okay. We have discussed noises. I mean, thermal noise, intermolation noise, crosstalk, and impulse noise, right?
Yes, sir.
Okay. Once again, quickly just say thermal noise is nothing but the agitation of electrons, thermal agitation of electrons, and it's a function of temperature. And we have seen this. I mean, it's called also called white noise, and it is significant in case of satellite communications. And we have seen this how noise can be estimated for a bandwidth of B. It is KTB. So in terms of dB watt, you can find out general problems are there. You must take care of all those things. Intermodulation noise, that is actually a generation of new frequencies because of nonlinearity. The nonlinearity may be in the transmitter or in the receiver or maybe in between the channels. Right, there can be some frequency or different frequency will be generated because of this nonlinearity, excessive signal strength, like these things. So that is intermodulation noise. We'll see in different cases these noises, limit the performance. That we'll see it. That is most important in intermodulation noise. Even in multiplexing also we'll see. Next, crosstalk. Crosstalk everyday life. You have the experience of crosstalk. I mean telephonic line particularly. It's a coupling signal coming from one channel to another channels. That may be within the two-state pair or maybe in a coaxial cables. Also, these things are there. And these noises are, see, intermodulation noise, thermal noise. These are actually predictables, right? Crosstalk, intermodulation, thermal noise are predictables, but impulse noise, that is that is the noise of very short durations. That may be due to fault or malfunctionings in the communication systems, just like say lightning, like these things. That times you see huge digital data can be lost, right? But it is not so problem in case of analog signalings that you have seen it. So in these connections, one more thing is there that you have to consider, that is a channel capacity, right? So far we have discussed transmission impairments. Things that you have to consider in data communications, transmission impairments. We have seen the types of the transmission techniques, analog transmission techniques, digital transmission techniques. And next we have seen these transmission impairments. Next you see the channel capacity. That is also another most important in data communications. And here actually it indicates the maximum data rate that can be transmitted, maximum data rate that can be transmitted over a communication channels, right? That is the communication channels. That means the meaning is this: for a particular bandwidth, you have to have maximum data rate, right? You see. So what you can say by definitions, it is actually if you I mean particular conditions, under given conditions, right? The maximum data rate that can be transmitted. This indicates the maximum data rate. Maximum data rate that can be transmitted over a particular channels or for a particular bandwidth for a given bandwidth, right? And you see, actually the limitation is here, right? The maximum data rate means, that means some limitation, some constant factor is here. That is actually the noise. So in this connection, there are two bandwidths generally considered. One is the Nyquist bandwidth. And another is Shannon's capacity. So in this case, this Nyquist bandwidth, it is considered in a noise-free environment. That means it's an ideal system. Any environment, practical mediums, always noise will be there. So, but it is considered it is the noise-free environment. Noise-free environment, right? In this case, the formulations of these limitations, you see here actually Nyquist bandwidth. If the environment is noise-free, then the limitation on the data rate, it is the bandwidth. right? And it states that as the Nyquist theorems, you can see it is if the rate of signal transmission is to be the rate of signal transmission. If the rate of signal transmission is to be, then you see then a signal with frequencies no greater than B is sufficient to carry the signal rate. Right. That means a signal of bandwidth B is sufficient. Signal, what I'm saying, signal with frequencies no greater than B. That means B is the bandwidth. So you see, the rate of signal, transmission is 2B. Then a signal of bandwidth B is sufficient to carry the signal rate. Signal of B bandwidth is sufficient to carry the signal rate. Or other way, you can say if the bandwidth is a B, if the bandwidth of a particular signal is B, then the maximum rate that can be transmitted, you see, that can be carried is 2B. So if the highest signal rate, that can be 2B. So for a particular bandwidth, of B, the maximum signal rate will be signal rate will be 2B. So what is the limitation actually? Why this limitation is here? This limitation actually because of the intersymbol interference that we have seen it, delay distortion that we have seen it, that is produced because of the delay distortions. So the limitation here is due to noise-free environment. So what is the then what factor will limit this bandwidth? That is actually because of intersymbol ISI, intersymbol interference. Intersymbol interference. So that is the limiting factor in this case, the constraint for this data rate, limiting factor. So say for examples of these the voice channels. So voice channels, if it is considered, it is say 3100 hertz, right? Bandwidth, if you consider the voice channels P signals, the bandwidth of 3100 hertz, right? Then you see the capacity of the channels will be that will be corresponds to 6200 bps, bit per second. So that will be the data rate for voice channels. Now, if you consider voice channels that transmits digital rate within a bandwidth, if the bandwidth is 3100 hertz for voice channel, if it is the bandwidth, then the maximum data rate, right? The capacity of the channels, the maximum data rate or the capacity. This is a capacity. Is or the maximum data rate. It will be 6200 bit per second. And of course, this can be enhanced if you consider the multi-level signaling. We'll see it. Multi-level signalings. Generally, signal schemes digital. If you see one pulse, one beat, but one pulse can also represent. Suppose we'll see next. We'll see it. Suppose this can represent 0 or 1, but some multiple scheme is here. This pulse can be represented by more than one bit, 0 0 like this, 1 0 like these things, right? So if this is multi-level signal, say 2 binary, 1 quaternary, 2 binary, 1 quaternary. These are multi-level schemes are there. We'll see it. Multi-level schemes. That times the capacity relation will be slightly different. It is for multi-level. These are most important for silly questions. That's what type of questions. So keep in mind these things. Try to understand also multi-level signaling. That is the Nyquist formula. It converts to, earlier it is C equal to to B, but now it is C equal to B log of 2 to the base M, where M is the number of voltage levels. Number of voltage levels. Number of voltage levels, right? Say for example, if M equal to 8, and if you use these some modems, say, then C will be, if you just calculate this C, it will be 18,600 bps for same bandwidth of 3,100 hertz. So for multi-level schemes, the capacity can be enhanced if you just increase the number of digital signal elements. Right. So that is the Nyquist relation. But of course, it is an ideal system because it will be valid in a noise-free environments. But if you see these things, you will see in multi-level scheme. Obviously, you can have more capacity, but at the same time, there will be a increased burden on the receiver also. Because see, receiver, if just two levels are there to identify 0 or 1s, that is easy task for the receiver. But if complex complex levels are there, I mean, if multi-levels are there, it will be complex. So heavy burden will be there on the receivers, but to distinguish the signal elements. So these things are there. This is for this is the Nyquist relations. Next, you see the Shannon capacity relations. Shannon capacity. In this case, you see here it considers the relations with the presence of noise. Of course, the noise, it is there are different types of noises you have seen, but only here white noise is assumed here in these relations. And in this case, one parameter is considered since noise is here. So signal to noise ratio, this factor is considered here. And here, the obviously the expectation is this: the signal strength should be high to receive the data correctly in presence of noise. Signal to noise ratio is most important. I mean, signal strength should be high than the noise. Then only receiver can detect these signals correctly, retrieve the data successfully. So the key parameter in Shannon's relations, it is the signal to noise ratio, and you see it is expressed in dB. It is SNR in dB. Signal to noise ratio is dB, and it is in dB. It is 10 log 10 of signal power by the noise power. These are the most important terms to determine the performance of any communication system, signal to noise ratio. So this signal to noise ratio actually sets the upper bound on the data rate, and maximum channel capacity in this case, it is C in presence of noise, that is C equal to B log 2 to the base 1 plus SNR. So log 2 to the base SNR. So that is the Shannon capacity. But of course, here also it is this is more practical than the Nyquist. But here also it is theoretical maximum. Just now I mentioned here only white noise is assumed, but there are other noises, white noise assumed here in this case. But other noises are also there, like say impulse noise, attenuations, delay distortion. Also those things are there. Those are not considered here in these relations. But it is more practical than the Nyquist capacity. So Nyquist capacity is a noise-free environment, and that times it is just twice the bandwidth the turret maximum capacity can have it. But in this case, it depends upon the signal to noise ratio. So this is the signal capacity. Well, in this connection, one more term is important. Concerning this the performance of data communications, that is like say SNR, EB by N0. EB by N0. That is also most important terms in, or particularly for digital communication systems. It is important for digitals communications. EB by N0, energy per bit. This EB is energy per bit, and N0 the noise per that we have seen per hertz, noise power density N0. So here, if it is EB, it is the energy per bit. Then you see, we can write it, if TB is the bit durations, then it is actually STB, where S the signal power, and TB the pulse duration. I mean bit durations. Time required to send 1 bit is the bit durations that we have seen it, bit durations, right? So it's the energy per bit. So that means R actually 1 by TB, the rate that we have seen it initially, right? We have discussed it, how to convert, how bandwidth and data rate are correlated. So you see EB by N0, with this we can write EB by N0, that is actually STB by N0, and I substitute this value of R, that is actually you see S by R S by R into divided by N0, so that is actually S by KT R. N0 equal to KT, that we know it when we have discussed it. We have discussed N0 for a bandwidth of 1 hertz transport density. So that is this EB by N0. So that, what is the meaning of these expressions? Here it tells us that if you increase the data rate, you see, to maintain the same EB by N0, you have to increase the signal power S. That is the meaning of these expressions, EB by N0, similar to SNR. And also we can correlate this EB by N0 with SNR. একটু ক্লাসে আছে এখন, জাস্ট আধ ঘন্টা বাদে করছি। হ্যাঁ, so right, so EB by N0, once again if we just write it, EB by N0, EB by N0, that is S by, we have seen it, S by N0R. This is N0R, and you know it, N equal to N for bandwidth of B, that is actually N0 times BT, say for a particular temperature and particular bandwidth BT, that is the noise for a particular bandwidth of B, right? Then EB by N0, this will be S by N, just substitute it, then is N0 will be N by BT, so it will be S by N into BT by R. So you see it, how S by N0 is related to EB by N0. Right. So this is the correlation between EB by N0 and S by signal to noise ratio. Another relation is important with this this capacity, that is, you can say that is with EB by N0, that is spectral efficiency. That is also used to determine the performance of communication systems. Spectral efficiency. Spectral efficiency. किसका मीटिंग होगा, कब होगा? नीचे लिखा, अच्छा Sorry, we discuss about the 23/7. अच्छा Okay. So spectral efficiency. In this case, you see S by n. If you write it, we have seen this S by n. It is you see in these forms, right? C capacity related to B log 2 to the base 1 by 1 plus SNR, right? So if you just write it SNR, then see S by N or SNR, central noise ratio, that will be from these relations. Say let us say this is say A, say from A S by N, you can write it 2 to the power, since 2 base is the 2 to the power C by B minus 1, that will be converted in these forms. So now we can write EB by N0, EB by N0, that is S by N into BT by R, right? So S by N, if you just substitute it here, so that will be 2 to the power C by B minus 1 into BT, if you just write it, and same B is here, so B by C. R also can be replaced by C. So that is the another relations which is widely used for determining the performance of the communication systems. Spectral efficiency. We'll see it particularly for wireless communications. We'll see this is the most important terms. So up till this we have seen these basic terms. Now we'll consider the transmission. If you have any questions, anybody, if you can ask. Next we'll see the new topic, that is the transmission media. If you have any questions, anybody? Any questions? Any questions quickly? If you have any question, you can ask.
No, sir. No, sir. Clear, sir.
Now see the transmission media. We have seen the transmission impairments earlier, capacity relations, we have seen it, Nyquist and channels. Now we'll consider the transmission media. We have discussed in the beginning, media can be two types, can be classified into two, guided and unguided. It can be guided or unguided. I mean, the information can be carried through guided mediums or unguided mediums, right? And if you consider these guided mediums, actually it provides the physical path. It provides the physical path. It's guided medium. It provides the physical path along which the signals are propagated. Right, propagated, and the examples are, you see, the two-state pairs, coaxial cables, optical fibers. These are the examples of the guided medium, right? And in case of unguided media, you see here, actually for unguided media, it employs antenna. Here antenna is involved. It uses antenna for transmitting the information through air, vacuums, or water, right? So in this case, the unguided medium uses antenna for transmitting the signals. And if you just see among these guided media, even if you consider this unguided media also, the optical fiber, it has a tremendous capacity, because you see here actually the carrier frequency, the optical signals, and that is around 10 to the power 14 to 10 to the power 15 hertz. A huge, very high carrier frequency is here. Because of these things, the huge capacity can be obtained, has been obtained in optical fiber. That's why you see much of the market for high-speed LANs or long-distance applications captured by the optical fibers, right? But some limitations are also there. So wireless, the advantages of if you use a mobile or even wireless device, then of course you need wireless transmission systems. But when you consider the capacity or bandwidth, then it will beat to any other communication systems. Anyway, in case of unguided transmission systems, unguided transmission techniques, if you just consider, here antenna is used, and here actually the three regions are there: broadcast radio, the techniques are actually in unguided media. Techniques are broadcast radio, another is terrestrial microwaves, and satellite microwaves. Satellite microwave. These are the unguided. Also, there is another wireless transmission is here, that is infrared. So these are the different transmission techniques used in case of unguided transmissions. But keep in mind, in case of guided mediums, you see medium itself is most important. Here medium is most important to determine medium itself. Medium itself is most important in case of guided mediums to determine the transmission characteristics. Right, medium is most important. But in case of unguided transmissions, unguided media, here the bandwidth of signal that is transmitted by the antenna is most important. Bandwidth of signal transmitted by antenna. Antenna is used to transmit or receive the signals. Right. So the difference you must keep in mind. In case of unguided media, bandwidth of the signal produced by the antenna is most important than the mediums to determine the transmission characteristics. Right. So keeping in mind with this, keeping in view all those things, now you see we can see the transmission characteristics of different guided media and unguided transmissions. To analyze the transmission characteristics, generally the two key constants are there. If you want to analyze the data transmissions, right, then you have to consider the two key concern or key factors are there. One is data rate, and there is, can you suggest what will be the other ones? Anyone? For in data communication, if I say the two important things you have to consider, the main components, key components for any data communications, one is data rate. Another, can you say anybody? Any other, can you suggest anybody? What will be the other component? Anyone? Quickly.
Sir, signal strength.
Signal strength, that is not the key concern. Signal strength is important, but that's not the key concern. Digital communication, okay, successfully you can receive the data. That is true, but that is not the key concern. Right. That is one of the aspects, of course, but not, you cannot consider the key concern. Like say data rate is most important. Suppose you want to establish a particular systems from here to America, like these things. So what are the things should be considered? One is data rate, another will be distance. Right, distance is most important. What is the distance? Right, the two important things are there. This data rate, another is distance. Right, these are the two important components to determine the data transmission characteristics, or if you want to design the data communications or data transmissions, then two things you have to consider. One is data rate. Other things also could will be there. What you are saying, signal strength, transmission impairments, everything would be involved. But the key constant you have to consider is data rate and distance, and many factors are there that will affect of these things. So if you see the factors that affect these things, what you are saying now, it will be one, the factors. Now the factors that affect these two these key components are: number one is the bandwidth. One is the bandwidth. So you can say greater the bandwidth, obviously greater with the data rate, right? This the bandwidth, that just we have seen it. If you consider the other factors remains constant, then if you increase the bandwidth, then R will be the data rate. That is once. Next, you see transmission impairments. Transmission impairments. Transmission impairments, we have seen it, and the most important is the attenuations that will affect the distance. Attenuations, we have seen it, that is most important among these, and this will affect the distance. And for guided transmissions, you know, the two-state pair, we'll just discuss it. Two-state pair telephonic lines, this suffers more attenuation compared to other guided medium, right? So this is another factors, I mean, that will affect this data rate and distance. Number three is the interference. Interference. It is I mean, important. Important in case of the unguided transmissions, but also can be a problem in the guided transmissions. I mean, if you consider the two-state pair or some two-state pair like these things, then also there can be signal couplings from one to the other. Interference. Interference nothing but coupling from one channel to other channels, and that is critical in case of unguided transmissions. And the fourth factor is also there that will affect these things: the number of receivers. Number of receivers. We have seen this, the link. If you consider the data transmission link, and then it can be a point-to-point link or can be multi-point links. Point-to-point links, very simple. One side transmitter, other side receiver. In case of the multi-point link, multiple links, multi-point links. That times medium is shared by many attachments. Means many stations will be attached. I mean, that times they will share the same mediums. That times one attachment means, if you increase one attachment, means more attenuation and more distortion will be there. So that will limit the distance as well as data rate. So multi-point link is a critical concern in this case. So the number of receiver also is important, that will affect the data rate and distortion. More distortion, more distortion, more attenuation means it will affect both data rate and distance. These things are there. So if you just compare these things in case of the guided transmissions, you can see the two-state pair. Two-state pair. Here you see the frequency range. It is generally 0 to 1 hertz, 0 to 1 megahertz, 1 megahertz, and the frequency range. The attenuation, it is around 3 dB per kilometers, 3 dB per kilometer, and the repeaters. It is repeaters. It is attenuations. It is the frequency range. repeaters are 2 to 3 kilometers, 2 kilometers in this range. Repeaters are required. Repeaters are required because to overcome the attenuations or distortions, right? Twisted pairs. In case of coaxial cables, the frequency range can be up to 500 megahertz. 500 megahertz. Attenuations, of course, it is more. In this case, it can be. Here it is. Attenuation is maximum in case of twisted pair, but at the rate of 1 kilohertz. It is 1 kilohertz, right? 1 kilohertz, right? And here it is 7 dB. It is less compared to, but at the rate 10 megahertz. 10 megahertz, right? And in this case, repeaters distance can be 9 kilometers, right? 1 to 9 kilometers. And if you consider the optical fiber, you see the frequency range. You can't imagine it. It is around 400 terahertz, 10 to the 14 to 15 hertz. You see, terahertz. If you see gigahertz, 10 to the 9s. Right. Next will be terahertz. So 10 to the power 12 onwards, that will be the terahertz. Right. 400 terahertz, and in this case, the attenuation is 0.2 dB. Just see it. 0.2 dB per kilometer. Very, very less attenuation can be, and more than 50 kilometers, 40 to 50 kilometers repeaters spacings will be there. Nowadays, you see, it can be 200 kilometers. There is no need of repeaters in case of optical fiber. That's why you see optical fiber is now capturing the whole market. Right. Just 2 minutes more I'm taking. So if you just consider this twisted pair, and you see this twisted pair, actually, what is this twisted pair? In this case, you see two insulated copper wires, actually, they are arranged in a spiral fashions, spiral patterns, right? And so you see the twisting is most important. Something like this, we just see. We have seen these telephonic lines are there, like these things, two insulated copper wires, like these things. But why twisting is twisted is there, that is most important to understand these ones. Hundreds of such one pair, but hundreds of such pairs will be there grouped together. Actual cables, hundreds of pairs will be there. You see it here, but the question is why this twisting is here. The twist is important in this case. Twist lengths, the twist one pitch, if we just consider, the twisting is most important. That is because if some interference or crosstalk is there, that will affect both the wires, right? So the receiver will be immune to the interference. So it will be unaffected by these unwanted signals. So that is the reason for this balance can be obtained in case of twisted pairs. So that is the function of these twistings. Twist length is also most important. We'll see it can be different types. Just have a quick look on these things. It can be, say, EIA, Electronic Industry Associations, if you say, they actually categorize these twisted pairs. Can be Cat3 cables, can be Cat4, can be Cat5. Nowadays, Cat6 cables are there. In your hostels, Cat6 cables are there. So the category 3, category 4, category 5, category 6, these cables are there, right? They're having different frequency range and different data rates. And also this twisted pair, it can be STP, shielded twisted pair, or it can be UTP cables, unshielded twisted pair. These are actually unshielded twisted pair. STP is very costlier. Shielded twisted pair to reduce the interference, and their applications actually, if you see telephone network, the STP cables are mostly used in telephone network, telephone system exchange to the telephone side. These are widely used. This twisted pair that you know it, right? Basically to support voice traffic, right? And this the voice traffic by means of analog signalings, right? Twisted pairs. These are actually designed to support voice traffic using analog signalings. But of course, I mean, digital data can also be transmitted by using modems in this case, right? But you see, not only for analog signalings, this can also be used for digital signaling also. So local area networks, just I mentioned data rate, these are actually for component networking, these are used. The data rates of the order of 10 Mbps, most common. Right? Anyway, today this much. Next time we'll see it, the frequency characteristics, twisted pairs, and we'll see the other things. Any questions? If you have any question, you can ask. 2 minutes. If you have any questions, anybody, you can ask. Anyone, if you have any questions. Okay, then next time we'll see it. 36, total 36 today. Okay.